Welcome to SilviCast, the podcast about all things silviculture. My name is Greg Edge,
And I'm Brad Hutnick.
and we are both silviculturists with Wisconsin DNR Division of Forestry and your hosts for today's show. Hello!
Hey, good morning, Greg.
Brad, I got a question. What is one of your favorite things to do whilst you're walking about the woods?
You know me, Greg. I love to do a million things when I'm in the woods.
I don't want to know about the million things, Brad.
Well, there are lots of things to do, but I really enjoy turkey hunting, but that's only a certain part of the year.
Mm-hmm.
I really enjoy like walking around, like checking out, like doing plant inventories. Those are really fun. And oddly, I really enjoy just regular inventory when we're kind of putting something into our reconnaissance, but it's maybe something slightly different than we wouldn't normally put in, like say like downed woody debris, things like that.
Hey, but you have a strange sense of what's fun, Brad.
Well, we're in the woods. What do you like to do when you're in the woods?
Well, I just kind of laid that question out there because I thought for sure you were going to say, I like collecting mushrooms
Oh,
and stuff to eat.
well, you know me. I love that. I mean, every time we go out, I've got a bag with me so we can bring something back.
Exactly.
Yeah. So no, that's a given. Anytime I'm in the woods, I'm kind of doing that.
I know on certain occasions you've made me collect like large quantities of various mushrooms and things
Oh, well, you were out there with me when we found golden oysters.
multiple times. Yes.
Yeah, and people don't realize those aren't a native. They're kind of escaped cultivation.
Hmm.
So I don't know. I bet any one of the mushrooms that we find they have unique flavors, they have unique textures, they have unique stories. It's just fun all around.
Another question, do you know how many species of fungi live in our northern temperate forests?
Uh,
It's another quiz question.
not I do not have a clue how many live in northern temperate forests.
Come on, make a guess.
You could say 3 million or if 3,000, it wouldn't make a difference. But would not have a clue. I would just say that it's a lot.
Okay, well, I don't have a clue either, so I couldn't even find
Oh, and you're pressing
I
me, and you're pressing me.
couldn't even find an answer to that question. It's not on Google.
Good Lord.
Sorry, you can't get it.
Yeah, all right.
I mean, it only goes to prove I'm no mycologist, but there's probably more species than we know. And to be honest, as a forester, it's not something that I think about a lot. If I can't see it, I can't measure it, my focus is probably elsewhere, to be honest.
Yep, yep.
But there is one class of fungi that is crucial to trees, and we probably should be paying more attention, Brad. And do you know what that is?
What is it?
Mycorrhizal fungi.
Ah, yeah, yeah, yeah. The wood wide web.
Oh, yeah. Now you're onto it.
Yep.
So we know that mycorrhizal fungi play an important role in allowing trees to uptake more nutrients and water, right? But does it go further than that? There have been a huge number of popular media stories talking about this subject, but what is the current state of the science? And what do foresters need to know about how this fungus impacts tree growth or how it could impact our management? So that's why today on SilviCast, we'll be exploring this subject with Justine Karst, Associate Professor and Mycologist with the University of Alberta, and Marty Kranabetter, Regional Soil Scientist with the British Columbia Ministry of Forests.
You know, this is one of those conversations I'm really excited about because, honest to God, I don't know very much about this at all. We're there, but we better start with the basics on this one.
I'm with you. We got to start with the basics. But Brad, why are mycologists the most virtuous scientists?
Oh boy. Oh, here. I'm afraid to ask. Why are they?
Because they're all obsessed with morels.
Oh, you couldn't let that rest, could you? This season of SilviCast is brought to you by the Nelson Paint Company, McCoy Construction and Forestry, and the Family Forest Carbon Program. You make the SilviCast world go round, so thank you.
Justine and Marty, welcome to SilviCast. It's nice to meet you both.
Thanks for having us on the show. Yeah.
Great to be here.
Hey, we're really excited to have you guys here today. because I think this is going to be a really interesting conversation.
I'm just going to warn you both right now that I know very little about fungi. And so we are going to have a remedial session here at some point.
Yeah.
Just saying.
I know Greg and I talking in the back, kind of getting ready for this episode. It's been like, man, I really got to bone up because this is all, it really is. It's kind of new stuff for, I think, us and hopefully for a lot of other people as well.
Yeah, well, definitely this topic, I mean, and we'll get into it, but one really exciting thing about it, though, is how it's got so many people into fungi in forests.
Yeah.
This whole conversation, and that's, I think that's a really important element. We can talk about, you know, maybe some of the places it's gone where it shouldn't has, but definitely just the interest, the public interest, I think, in forests and fungi has been really exciting for all of us that do study forest fungi.
Yeah.
And it's something that foresters should know more about. Really.
And for me, I, like a lot of people, I was just got interested in the nice edible fungi you find in the forest, right? And that's sort of your gateway into this whole world of below ground ecology. And it just draws you in.
Mm-hmm. But before we dive into that, we should just do some introductions here for our audience. So, Justine, maybe you start first. Could you just say who you are and what your job is?
Yeah, so my name is Justine Karst. I'm an associate professor at the University of Alberta in the Department of Renewable Resources. I study the mycorrhizal ecology of forests, and I've been working on this topic for, I guess, about 20 years now.
Cool. Marty?
Yeah, I'm Marty Kranabetter. I'm a regional soil scientist with the BC Forest Service. I'm currently located on Vancouver Island, Victoria, but I've spent a lot of years in the interior in Prince George and up in the northwest in Smithers. So I've seen a good chunk of the province now. And I'm not really a mycologist, I have to say. I'm a soil scientist with a special fondness for fungi. And my mandate is to do mostly sort of applied research rather than fundamental research.
Mm-hmm.
I wanted to point out also, so the way that Marty and I know each other is that we are at University of British Columbia at the same time working on our PhDs.
Oh,
so
yeah.
Cool.
we go way back. Yeah. Yeah.
Well, that's great, especially having some guests here from Alberta and BC. I'm really psyched about that. We tend to sometimes stay in our little bubble of the lake states, so it's always great to get out beyond that and get new ideas and thoughts.
And maybe we could start, I know, like we talked about, we're starting from basics. So maybe for people out there who haven't heard about some of the recent research and some other things, we're starting to think now about fungi as being really important in forests. But why is that? Why is this conversation coming up now?
Do you want to start, Marty?
Okay. Well,
Yeah.
I think this momentum's been building for a few decades. When I started getting interested in this topic, kind of the late 80s, early 90s, it kind of opened my eyes to this below ground symbiotic community that was kind of almost seen as a house of cards. Like people felt it was very vulnerable, and any poor management decision might really hurt our forest ecosystem. So I was immediately drawn in. As a research scientist, we need to know more about this. We need to get on top of this. And I think, we've done a ton of research since then. And I think now we have a better sense of just really how resilient this community is. And some of those fears were probably overstated, but we're also just learning more and more about how fundamental it is to how an ecosystem works. The symbiosis is the basis of any forest ecosystem. And it's something we can't necessarily manage, but to understand it and to protect it seems to be really important.
So we're kind of recognizing all that. And I think today we're going to delve into one particular type of fungi that we find in our forest, but we do have like a range of different type of fungi that we find in forest, correct?
Yes. So the one, and actually Marty probably studies more of the range of fungi than I do. So I focus on mycorrhizal fungi. So these are fungi that grow either in or around root tips of trees and other plants. But then there are also the saprotrophic fungi, and those are the decomposers. And so with the mycorrhizal fungi and the saprotrophic fungi, they often will form the little mushroom, well, sometimes big mushroom fruiting body that most people will think of when they think of fungi is those mushrooms in the forest. And then the other type is pathogenic fungi, which also can form these mushrooms as well. So those are the three main fungi that will be out there in the forest. And then, of course, their functions are very different. Mycorrhizal fungi are really important in acquiring nutrients, water for trees. The saprotrophic fungi are fundamental because these are the decomposers that are recycling nutrients. And the pathogenic fungi also play a really important role. I mean, sometimes we might not like them because they're killing trees, but that death of trees is also a really important part of forest ecosystems, like that life and death continuum. Anything else, Mari? Did I miss a type of mushroom or fungi?
Well, we could, if we want to get into the details a little bit more, there are two really important types of mycorrhizal fungi. So there's the ectomycorrhizal fungi, start using some Latin words here, and that's the one we associate with our coniferous forest, so pine, spruce, fir, hemlock. A lot of our commercial tree species are ectomycorrhizal, and then there's these arbuscular mycorrhizae, which is it's similar in that it's a symbiotic fungi, but it's a different class of fungi, and they tend to be on some of the cedars and some hardwood species, like more in the eastern US. I'm not as familiar with them. But so anyways, there's just two fundamentally different types of mycorrhizal fungi in our forest, on our trees. So that it's an important part of the ecology as well.
Thanks.
And do they perform a different function for trees then, or the different species?
Yeah, that's actually a huge research initiative from the last 10 years or so. People have been exploring this a lot. And the general idea is that the ectomycorrhizal fungi, there's just so many species, like it's a really, really diverse guild, and they have a lot of attributes related to enzyme. They can mobilize nitrogen, they can mobilize phosphorus, they can get their hold of cations, they're good at water. And the arbuscular mycorrhizae tend to be less diverse and more of a scavenger type role. They seem to just kind of take what they can from the soil and not necessarily make it happen, like mobilize or sort of mine ecosystems. So they occupy different habitats to some degree for that reason.
I remember, Justine, we had done some work here in Wisconsin on our biomass harvesting guidelines, and we were talking about the decomposers primarily within that, and just remember reading research about the huge variety of species. Is it known like how many species of fungi we have in the forest, or is that something we're still exploring and learning?
I would say that we're still learning about that. So the mushrooms that you see above ground, or like say the turkey tails and things like that, the ones that are macroscopic, we can ID those. And to be honest, some of them are tricky to ID morphologically, but there's many that occur in the soil and we don't know. There's a high number of fungal species estimated that are to remain discovered. Like we haven't ID'd them yet. So there is a lot of, I think, unknown diversity. But to say, I think though, like say for ectomycorrhizal fungi, I think we could do a decent estimate of how many occur, say, in a stand. And I think, and Marty can argue with me on this, I would say it's around hundreds probably in a stand that are growing on the root tips. You won't see them all as mushrooms. Some of them might just stay below ground and not pop up for a long time, and others might.
Yeah.
So, you kind of have to be careful about using the number of species you see above ground to say how many are below ground. But my guess is probably like hundreds with the ectomycorrhizal fungi, and then maybe hundreds as well with the saprotrophic fungi. What do you think, Marty?
It depends too on the stand, of course, but
Yeah.
if you have multiple host species in the stand, so let's say you've got a nice boreal stand with pine, spruce, and fir, you'll definitely have probably hundreds in a few hectares of forest. Whereas if you just had pine, less, I would guess. But yeah, the diversity really is ridiculous, right? Like, why so many species? That is one of the questions we started asking probably 100 years ago, and we're still asking today. Why are there so many species? It's insane.
Mm-hmm.
And saprotrophic fungi would be similar. Like, there's just so many, and it's harder to we have all these molecular methods now where we can sort of pull out the DNA out of soil. And so we're still kind of grappling with that. But yeah, the numbers are outrageous, really.
Are species widespread in distribution, or are they found in like localized places only?
Both. There's some very cosmopolitan species that you can find all over the world. And then there's some that are much more specialized, more localized to certain habitats. And we kind of think those species that are more localized might be have a higher fitness for that particular habitat. That's another area of ongoing research. But yeah, it's a real mixed bag that way.
Kind of like the tree species. You can think of some that are very localized and then some that are all over the world. And it's the same thing with the fungi. Yeah.
Justine, one of the things that kind of brought this subject to Brad and my's attention was a paper that you did in, I think it was Nature, Ecology, and Evolution about mycorrhizal networks. And so in that paper, you had this term that I guess as a forester, I'm not familiar with, common mycorrhizal networks or CMNs. So can you explain what those are?
Yeah. So common mycorrhizal networks is what is formed when mycorrhizal fungal hyphae. So the hyphae, you can think about a mushroom and it is made of hyphae. And then below ground, the hyphae form, the kind of the spider webs that you see in the soil when you dig up the soil and you can see those threads. Those are fungal hyphae. Some of them will be ectomycorrhizal fungal hyphae. Some of them will be saprotrophic. But yeah, all that kind of webby stuff, that's the fungal hyphae. And sometimes that fungal hyphae will connect roots of the same or different plant species. And when they do that, we say that a common mycorrhizal network has been formed. So this, in common mycorrhizal networks, there's sort of like a subdiscipline within the broader discipline of mycorrhizal ecology. And they're really interesting. It's really fascinating to think about this, like plants being connected below ground through these fungal threads. And their function has been of a lot of interest to scientists for decades and decades. And obviously to the public as well, I think more recently, about what are these CMNs doing in the forest.
Yeah, and Brad and I, just like the rest of the public, we read and see this sort of terminology and this topic discussion in tons of different places, especially in the last few years. And so some of these CMNs or kind of the science around them is controversial. Why is that?
Yeah. So one thing I should clarify, most of the public probably has not heard CMNs or common mycorrhizal networks, but they've heard of the Wood Wide Web. Is that?
Yeah,
okay.
Exactly. Yeah.
So that's probably where more people will connect into this conversation.
Or mother tree is another one that the public really glommed onto.
Mother tree. It's kind of all part of the same working metaphor. And the Wood Wide Web, it's not the same as a common mycorrhizal network. The Wood Wide Web is this metaphor, this idea that I would say trees are connected below ground and sending signals to each other and resources and taking care of seedlings, and the mother trees are taking care of their seedlings through these common mycorrhizal networks. So in science and research, we tend not to call it the Wood Wide Web. We call it, like common mycorrhizal networks.
Yeah.
And the reason it's so controversial, like before we even talk about maybe why, what's going on in the public with it, but in the research community, it has been controversial for decades in terms of what the functioning is of these common mycorrhizal networks. I think that most of us agree that it's very likely that they're formed in forests, that trees are connected below ground by mycorrhizal fungi. There's probably debate on which trees, how many trees, how long these connections stay. Do they even exist long enough to be functional? Because you can imagine in the soil, there's lots of things that eat fungi. And so even if a connection is formed between two tree species, they're probably often going to be broken and disturbed and that kind of thing. But I think most of us in the field would say, yes, it's very likely that trees and seedlings could be connected by these common mycorrhizal networks. But where the debate really ramps up is, what are these common mycorrhizal networks doing, if anything? And this is where we get into the discussion of, are they moving resources between trees and seedlings or between trees? Are they signaling to one another? When a tree seedling plugs into this network, does it do better if it's plugged into the network than not? And these questions, they've been going on, they've been present for, like decades. It has not been resolved. But I think what has happened is, over the past few years, the way that these stories have been told is in a way that it sounds like it has been resolved, and there is consensus that all this stuff happens. And I think for me, that's when I started paying attention a little bit more about what was going on in the public. What were people talking about? Because some of the claims that I was hearing, I was like, that's extraordinary. I
didn't know that. Yeah.
I didn't know that. Like, where are these studies? Like, geez, I am missing out here. I am not aware of these studies. And I think the public, I was, kind of fascinated. Like, where is this coming from? And that was part of the catalyst for this paper. That was part of it, but not all of it. Was just to, like, for Melanie Jones, Jason Hooks, and my two co-authors, that was definitely one of the things that kind of got us thinking that we need to review the literature, because we're behind. We don't know where these claims are coming from, and we need to get up to date. So that's partly what prompted it. The other reason was that, so Melanie Jones, she was my PhD advisor. She just recently retired, and she was involved in one of the kind of groundbreaking studies on this topic, this one that was put out in 1997 in Nature, and it's actually where this Wood Wide Web term got coined, was from this study. And over the years, she had noticed that her papers on the topic, that they were getting miscited. It's like, they found something, they had results in the paper, they discussed them, but the way that they would get interpreted by other scientists was kind of deviating from those results. And she's getting a little concerned about that. So that's what drove us to, like, okay, we need to look at this topic again. And so the paper started it came from a very innocent place. We didn't go into the work to, like, debunk the Wood Wide Web. That's not what started it. It was really, we're hearing these extraordinary claims, like everybody. What's the evidence for these claims? And that's what we wanted to know.
What I find interesting about this discussion and this aspect of forest management is that it seems like it's grown. And so now there are these anthropomorphic kind of implications. Like, if this is the way it is, then it kind of changes our understanding and maybe drives us toward different versions of management. And you see people advocating that, but then looking back at those roots of it again, it's like, well, wait, how firm is the foundation that we're actually standing on? And so that, I think, is just really fascinating.
Yeah. Well, I think for us too, it was just like, it was surprising how thin the evidence was in some cases. Well, for some, there was just no evidence at all. But yet this big story has developed. And I think part of the reason that this big story developed and could develop is because it's such a feel-good story, right?
Yeah.
This idea of mother trees taking care of their seedlings, and this below ground fungal network that is working for the trees, and just these passive conduits and serving the trees. Like, it's a very nice, warm view of the forest. So I think that's part of the reason it just took off.
And I think the other challenge with all this is the science itself is very difficult to do, right? So a lot of times they use labeled carbon isotopes, and they'll have a receiver seedling and a donor seedling, and you use C13 and C14. And you try and see if some of that label shows up in the other trees. Or we bury seedlings or root systems in these mesh bags of different sizes, and there's all kinds of confounding issues, like, does the mesh bag affect the soil moisture or the nutrient supply, or so we're trying to draw conclusions from very, very difficult science. And sometimes I think people, like in the carbon isotope one, you finally get some carbon isotopes showing up in your receiver seedlings. So you say, yay, it's significant. That means it's happening everywhere all the time. We've just changed the forest ecology paradigm, right? And so that's the risk as scientists. We want to feel good about our science. We want to kind of run with it.
Mm-hmm.
Some of the other papers that have come out as sort of a companion to Justine's have also looked at some of the CMN stuff. And one angle I thought was interesting was they sort of looked at it more empirically, like this claim that seedlings are raised by their mother tree. Well, most of the literature shows that seedlings do, when you just like, never mind isotopes or bags or anything like that, just look at regeneration patterns, and mostly they don't regenerate very well close to mature trees, right? They regenerate better away from the tree. So when you see things like that, you think, well, wait a minute, that's not supposed to happen.
Yeah. It's funny because I always use the analogy that trees would be like really bad parents. They were like, get out of the house, like go away.
Yeah.
I'm not going to support you. And then all of a sudden it's like, wait, they're really good parents.
I was just thinking, we have a hard enough time studying things that are above ground. I just can't imagine the difficulty in studying this below ground. And are most of those methods done in like a greenhouse sort of setting? Or I could imagine it's even more difficult in a natural setting to kind of tease out what's going on in those situations.
Yeah, there'll be a combination. Like there are greenhouse experiments and there are field experiments. And in our review paper, we really focused on the field experiments because when we're talking about the effect of, big adult trees on seedlings, you can only do that in the field.
Mm-hmm.
You can't run that kind of experiment in the greenhouse. And when we did our review, we actually, it was surprising. And there were more studies than we thought. Like I think there was about 12 field studies that looked at the possibility of resource transfer through common mycorrhizal networks. And I want to say about 14, 15 that looked at the effect of common mycorrhizal networks on seedling survival, growth, that kind of thing. Actually, Marty, he has done one of those experiments. And when we were working through all of them and gathering field experiments, Marty's really stood out in that it was the longest running CMN experiment we could find. It was 5 years. Most of the experiments, mine also included, they go for 2 years.
Mm-hmm.
But Marty's right. Like these are really, really tough experiments to run. And so when we were writing up the paper and looking at these past experiments, it wasn't necessarily like, oh, these experiments were done poorly. That was not really our message. It was more like researchers did the best they could for that time and for these kinds of experiments that we are only able to do because it's field work and everything else. And these questions are really hard to answer. But maybe, or not maybe, but what seems to have happened is in some cases, the results have been overinterpreted, overextended. The uncertainty hasn't carried forward. Alternative explanations haven't been carried forward, especially in the public. And so they get a sense, again, these are all like dialed. Like we know what these results are and they're really clear and they're really strong and they occur in every forest. And it's just so far from reality. So it's that kind of stuff I think that has been missing from what the public has heard. And of course, and just the way that these stories have been shaped, again, is just missing a lot of kind of that detail. And in some cases, just recognizing there have been no field experiments on some of these claims. Like we don't even know. We don't know what's happening in a forest. And that is a guess, in terms of, say, this claim about mother trees sending signals to their seedlings through a mycorrhizal network, like defense signaling. That has never been tested in a forest. And yet you can find infographics, videos, like showing this idea that mature trees are signaling to their babies. And that was really surprising to us. Like it's never even been tested in a forest. We don't know. We simply don't know yet.
The other thing that I find interesting is that there hasn't been that, like Justine said, there hasn't been that many field experiments. I did one. And a lot of us that tried to do a field experiment, I was a big believer when I started mine after that 1997 paper came out. And so I put seedlings in this dark understory under different size mesh bags. And the results were opposite of what was supposed to happen. The more the finer the mesh, like the more independent the seedling was, the better it grew. The more it was not attached to the other root systems, the better it grew. And when you look at these reviews, a lot of these studies are showing the opposite of what are supposed to happen. Like the worst performing seedlings are the ones that are in full root contact with the surrounding trees. And that's the part that I always thought was interesting. Is that okay, but we're actually not proving this over and over and over. We're actually not we're sort of confirming it might not be true. And yet that evidence kind of gets shunted aside, I think. Like that's not interesting. You probably did something wrong. and so yeah, I think we highlight the few times where it worked and sort of ignore many times where it didn't work.
Mm-hmm.
If I'm hearing you guys right, it sounds like there's a little bit of misinterpretation, and you guys aren't saying that it's necessarily wrong, but you can't prove that it's right. Is that correct?
Well, in some cases, I would say, so yeah, definitely misinterpretation. But I think also I want to echo what Marty is saying, that there is evidence for the opposite. So, for example, this idea that resources are transferred through a common mycorrhizal network between trees and seedlings or whatever. In some of the experiments, people have shown that small amounts of resources do move below ground, but in the absence of a common mycorrhizal network. And so,
okay,
so there is evidence that shows, resources do move, but they don't need a common mycorrhizal network. And so again, it doesn't necessarily say they can't move through a common mycorrhizal network, but it doesn't need to be in place for this small trickle of resources to move around. And the other thing too, sort of on Marty's note, is that we can show that in the absence of mycorrhizal networks, seedlings do better. And so there is evidence on that point that the common mycorrhizal network or access to it can be detrimental to seedlings if we sort of take the experiments at face value. And another thing that we found too in our review was that only in 18% of studies of looking at how seedlings do in response to access or not to these common mycorrhizal networks, and only 18% did the common mycorrhizal network have an effect above and positive that canceled out the effects of root competition. And in the vast number of studies, there was no effect. Like if the seedling had access or not to a mycorrhizal network, it didn't affect seedling survival and growth. So there actually is a lot of evidence that is counter to the story. So it's more than that. I would say it's not that we can't prove it. It's just that no, there are studies that
okay,
have evidence that do show opposite to the story, but they tend to get buried in terms of what gets pushed forward in the science, what the public hears, because I don't know, it's like people don't maybe like the idea that trees compete. And, and I'm not saying that that's the only kind of interaction that happens in forests, but it is a really important interaction that we can't dismiss. There's some situations that there is more facilitation going on, for sure. But this story that trees, live kind of in harmony together and in families, like it's just not well supported when you actually drill down in the evidence. And then in a few cases, like the one that I said with the trees signaling defense signals to each other through the common mycorrhizal network, that is an instance where there is no evidence because it hasn't been tested. And I think you're right, though, it's being careful to separate, how's it go? The absence of evidence is not necessarily the absence of an effect versus you can have evidence for the absence of an effect. And we're kind of sitting in both places with the mycorrhizal literature in terms of how or what mycorrhizal fungi are doing in forests.
Justine, I just wanted to just back up and clarify something because I think that maybe helps me understand this conversation. And that is in that paper, you looked at 3 claims, right?
Yes.
Kind of 3 major claims. And so the first one was CMNs are widespread in the forest. So that was kind of that broad claim of they exist and they do happen.
Yes.
And that one, you said there's evidence for that. We found evidence that they do exist.
Yeah, no, and I think, it'd be good to have Marty's input on this too. I think most of us agree and understand that these below ground connections can be formed. But I think that claim was more in response to this idea that there's this below ground internet and all trees in the forest are connected below ground. And that's sort of what we were responding to. But that idea is vastly different than when you think about fungi. Like some of them below ground, they grow like little tiny patches. And so there might be a couple trees that are connected by this fungal species. Other fungal species, they form genets or individuals that are really large. And so maybe in that case, there's a bunch of trees that are connected. But it's really like I've heard it described much more as a mosaic, not like as an internet.
Mm-hmm.
And I think the public pictures it as kind of like the plumbing in your house, like it's somehow permanent, right?
Yes.
But these feeder roots that have these mantles, they only live a year or two at most. So there's a tremendous amount of turnover in the roots. And every time a root system dies, you have to assume if there was a link, it's gone now. It might relink when it regrows. And as you mentioned earlier, there's tens of thousands of columbella and mites in soils, and they're constantly grazing on fungi. So between roots dying and fauna eating fungi, I always assumed that this fact, if it happened, was very transient, wouldn't last very long.
Kind of like in the above ground forest, we call it a shifting mosaic, right? Things are always moving and shifting in these patches.
Yeah. So it's very similar below ground. But, with the caveat, like it's one thing, when you're doing your tree surveys, alive, dead, size, canopy extent, that's all really easy to measure. But below ground, that was really, really hard to quantify. It's very difficult. And so it is still kind of a black box down there in terms of like the sizes of individual fungi, yet turnover. Like we just don't have a really good grasp on it. But I think it's fair to say, it doesn't work like the plumbing in your house. Like Marty, it doesn't work like that. Yeah.
Maybe like the plumbing in my house.
I guess it depends,
we don't want to discuss the plumbing in your house, Brad. The second claim, Justine, that you were looking at what the science is do CMNs transfer resources to increase seedling performance? And so what kind of is the status of what we know on that front?
Yeah, what our conclusion is that there is no definitive demonstration of resource transfer happening in the field. There's alternative explanations. Like I said, there's experiments conclusively showing small amounts of resources can move below ground in the absence of a common mycorrhizal network. And this idea, and Marty alluded to this at the beginning of the podcast. So there's kind of two ways that we look at this question. We use what we call a natural barrier approach. So to look at resources moving, we can have an ectomycorrhizal tree, say an arbuscular mycorrhizal tree, and another ectomycorrhizal tree. This is the way this experiment that we've been talking about in 1997 was set up. And then you can label one of those trees. So the carbon dioxide that is being photosynthesized has a label on it. So you can track where the carbon goes. Does it go to the next species? Does it end up in the ground or whatever? And so that experiment's done, and it was a very, very novel way to look at this question, with the idea that if you see carbon label moving from an ectomycorrhizal tree species to an arbuscular mycorrhizal tree species, the only way that that carbon can move is through what we call the soil pathway, because those two species, they can't form a common mycorrhizal network because they have different mycorrhizal types. Those fungi cannot fuse between arbuscular and ectomycorrhizal fungi. So it's like a natural control to see how much carbon just kind of moves below ground versus how much carbon moves between an ectomycorrhizal tree species and another ectomycorrhizal tree species. So again, it is a really novel development, but a limitation of it is that these two types of mycorrhizal fungi, they're very different in that ectomycorrhizal fungi, they put out a lot of hyphae in the soil. They're pretty dense. Arbuscular mycorrhizal fungi, they don't put out so much hyphae. So if you can imagine, if you took a little drop of a resource and dropped it in the soil, it's going to be taken up a lot by ectomycorrhizal fungi, but not so much by that arbuscular mycorrhizal fungi. So by using that arbuscular mycorrhizal tree host as a control, it's likely to vastly underestimate how much carbon is just moving through that soil pathway versus the common mycorrhizal network. Kind of that's an example of like, so we don't really know, is that carbon, was it just moving through a common mycorrhizal network? Was it moving through other pathways? And that's what I mean. It's just not that conclusive. And then the other kinds of experiments that we run, and myself included, Marty has done these too, is we put seedlings in these mesh bags. And the mesh bags, they differ in their pore size. So they'll either allow seedlings to form these mycorrhizal networks, like plug into the network, or not, access to neighboring roots, and you can do all combinations with it. But there's potentially confounding effects with those bags. Like they could change the fungal community composition. They can change how much fungi kind of can grow in that bag. And if they can't grow out of the bag, that might limit what access the seedlings, or what nutrients the seedlings can access. So all this to say is these bags can affect other parts of the soil and ecosystem that the seedlings might be responding to that have nothing to do with common mycorrhizal networks. And so for all these reasons, we said, the resource transfer is just not conclusive. We don't know. There is a couple of nice lab experiments that would show like, yeah, there's some carbon moving around, but there has been no study that I know of in the field that has shown that this little tiny amount of resource that might be moving through these common mycorrhizal networks has any ecological relevance. And what I mean by that is there's no experiments in my mind that have shown that that little amount of resource has any effect on seedling survival or growth. There's very few experiments that have put those together, and the few that have not shown that that little tiny amount of resource moving has any ecological relevance.
And I think that criticism was raised right after that 1997 paper was published. People are saying, okay, you managed to find carbon moving from one thing to the other, but does it matter? Is it just a drop in the bucket?
Yeah.
And there's a long history of trenching studies where they trench around a tree, and they weren't studying CMNs per se, they were just looking at root competition. But I think it was Coombs and Grubb reviewed 40 out of 47 trenching experiments. The seedlings grew better after the trenching, So all this empirical evidence would suggest that, yeah, maybe a little bit of carbon's going back and forth, but it's not changing the fundamental dynamic, which seems to be competition for scarce resources, light, water, nutrients.
Yeah.
Well, that's fascinating. We also had a third claim that you looked at, and that was that the mature trees were preferentially sending resources to seedlings, or kind of letting them know something's wrong in the neighborhood.
Yeah. So I think for us, like, that was the one that fell into the extraordinary claim. As a PhD, or as a graduate student sort of growing up in this field, I always knew there was debate about the carbon transfer and all that. Like that, it wasn't really new. So always knew there was debate on that. But this new claim, we just thought it was extraordinary. And then when we looked into it, and we did a pretty comprehensive review and check in the literature for support of this, and we could not find any published peer-reviewed studies that examined this claim that mature trees are sending signals to their seedlings through the common mycorrhizal network. It just didn't exist. And what we did find, though, is that it seems to be based on a greenhouse experiment. So this greenhouse experiment, with some seedlings grown in pots. It was a ponderosa pine and a Douglas fir. And they manipulated whether the two seedlings in the pot could form a mycorrhizal network or not, or if their roots were interacting or not. And then I might get it mixed up now. I think it was the Douglas fir, then that they either cut off the needles or added some bugs to it or whatever, and then measured the ponderosa pine to see if it changed in its defense enzymes. And what they found is that when the seedlings could form a mycorrhizal network, that when the Douglas fir seedlings were attacked by bugs or the leaves were cut off, that the defense enzymes were upregulated in that ponderosa pine seedling in the pot, which is pretty neat. Like it's a pretty, that's a pretty neat result. But what's important in that study is when the seedlings could form common mycorrhizal networks and their roots were allowed to interact, which is the situation you would find in a forest. You do not find common mycorrhizal networks in the absence of root interactions. So this is, in my mind, the most relevant treatment to what we would see in a forest. That effect was completely canceled out. So the Douglas fir seedlings, losing their needles or whatever else. And then the ponderosa pine, it's like nothing happened. There was no elevation or upregulation at the defense enzymes. So it's hard, kind of on two accounts, it's really hard to see how results of this greenhouse could be extrapolated to a forest. Because number one, these are little seedlings growing in a pot. And when you hear the story, what's often depicted, again, is these big, large trees. And, and I would argue, and I think Marty, he would agree, that using results from a greenhouse study then to inform what's happening in an old growth forest, it's totally inappropriate. And then the other point too, the treatment that is relevant when the seedlings can form mycorrhizal networks and when the roots are interacting, there was no effect. There was no change in the defense enzyme regulation. So to me, again, this is another point of so the results of this greenhouse experiment, how do they even apply to an old growth forest? And that was pretty surprising to me, honestly. It was just when we looked at it and just this seems to be what this claim is based on. And it was kind of sad too. It's just what happened? how did we get from this greenhouse experiment
point A to
how did this happen? And not just with scientists, but the public and the journalists, the reporters, everybody. How did this happen?
Mm-hmm. Yeah, like you said, it's a great story, and so maybe it's growing from kind of like some stories do. It's kind of growing from that.
Mm-hmm.
Yeah, or maybe it's something you want to believe.
Yeah.
But can you prove it? That's the other. There are always things that's boy, I'd love to believe this, but I just can't. How do you prove it?
Yeah.
Looking for continuing education credits? Check out the SilviCast webpage for more information. And now, back to our show.
Brad and I sitting over here in the eastern side of North America, we hear these studies about Doug fir and ponderosa pine, and maybe you know this and maybe you don't, but is there much work going on in, say, eastern hardwoods in what mycorrhizal fungi are doing in those systems?
Well, Marty might know, just in terms of mycorrhizal fungi, I think for sure there's studies going on that, what the mycorrhizal fungi are doing in the forest.
Just their general function and lots of stuff on. There's a lot of interest in carbon dynamics, how mycorrhizae affect soil carbon dynamics, whether a ectomycorrhizal tree sequesters more carbon in the soil than an arbuscular mycorrhizal tree. A lot of that work going on all over the world.
Mm-hmm.
Mm-hmm. Yeah.
But then, for the common mycorrhizal network research, there was only 2 studies that came up in our review. So one of them was done in a sugar maple forest in Quebec. And then there was another study done kind of a mixed hardwood and pine forest in Connecticut. So, so 2 studies.
Go east. Yeah.
Go east.
But definitely, I think it was 35% of the studies, the CMN studies that were in Douglas fir forests.
So this kind of boils down to, Brad and I, we work with foresters and forest managers and talk about silviculture. So based on sort of our current scientific understanding of these CMNs, are there any modifications, if any, we should be thinking about our silviculture above ground in relation to this, or to protect those communities? I guess, what does it mean for management at this point?
I think there's 2 things. So there is the CMN issue, but then there's the importance of mycorrhizal fungi. And often they get, sadly, conflated. So common mycorrhizal networks, obviously, they're made of mycorrhizal fungi. But our conclusion from our review is just the evidence is too scant, it's too unsettled to make any management decisions based on common mycorrhizal networks. That's what we said. But that is very different than talking about management decisions that do take into account mycorrhizal fungi. And so Marty's work, his research looks a lot more into that topic. So I'm going to throw that to him.
Well, yeah, thanks. I'm a big proponent of retention forestry, right? And this kind of came out of the Pacific Northwest about 20, 30 years ago. I think Jerry Franklin and some of those guys were a big part of it. This idea of leaving blobs of mature forest in your openings, trying to sort of create that natural structure you would get after a wildfire where you don't just kill every single tree. And we've done plenty of studies that have shown these lifeboats, that's what they call them, you retain these late cirral communities, these fungal communities. So there's a pretty strong effective stand age on ectomycorrhizal communities and diversity, and we generally assume our late cirral stands have the greatest number of species and a lot of really infrequent and beautiful species like these coral fungi. So, if you're as a goal of as a forest manager is to keep all the pieces, as Aldo Leopold used to say, we big push for retention forestry, old growth management areas, parks, all that kind of stuff. Keep some of that mature forest in your landscape, and then that's really just biodiversity. We just want to, we came into this watershed and there were 300 species when we got here. And when we leave, we want to make sure there's still those same 300 species, right? And then the other piece to that, as I was saying earlier about the endemics or the specialist fungi, there is some evidence that a lot of these really fungi that might be quite important to how the ecosystem functions, they don't necessarily come in right after disturbance. There might be a bit of a lag, like maybe they're coming in, colonizing those young forests like 30, 40, 50 years. So by doing retention forestry and kind of keeping that inoculum nearby, I think we're just reducing the risk of oversimplifying the community. If you have these massive cutovers, no old trees anywhere, and you're doing short rotations, 3, 4 rotations in, my fear is that you end up with such a simple community of these really generalist, cosmopolitan species that you do start to unravel some of that specialized function that these fungi have been doing for millions of years.
That's interesting. Do we need to worry at all about, and while you were mentioning that, I was thinking, does soil disturbance come into play as a part of thinking about CMNs? Because here in the lake states, we use scarification. We kind of avoid, in some situations, kind of soil disturbance. I'm curious what your impression might be on that.
Well, I think it's quite likely that those kind of mechanical site prep treatments can have an initial effect on the mycorrhizal community because you're removing some of the forest floor and having this mineral substrate. But I would guess that that's a reasonably ephemeral issue, and that as that stand matures, you're pretty much going to get back the fungi that belong there. So I don't think it's something I would be overly concerned about. Another one is fire, where there was always questions around broadcast or prescribed burning. Does that change the soil in a dramatic way? And a really, really hot fire could definitely take a while to recover. But I think in the end of the day, nature's pretty resilient if you give it a chance. One of my biggest things is just rotation age. I just think all our ecosystems are adapted. We have these patterns of succession, and they're well adapted to this sort of normal age of a forest. And when we greatly shorten that age, like we do on the coast, like we're talking about a 50-year rotation for the coast, that's where I think we really start to gamble on some of these processes. We're just hoping they'll stay intact over multiple rotations, but maybe not.
Do you know, Marty, sometimes we talk about different kinds of retention, dispersed retention of trees versus an aggregate retention. And sometimes we think or say aggregate retention or islands that are left undisturbed are probably a little bit better for various reasons. In other words, maybe they're retaining more species within them because they are not getting any equipment run through them or anything like that. So is there any effect, I guess, on the below ground community on doing aggregate types of retention?
Yeah, I've done some work on that as well and looked at island size. And you're right. We have what we call a fragmentation effect in that when you have small patches or even individual trees, you tend to change the temperature, moisture, the abiotic environment. The more edge you have, the more you change that abiotic environment. And I was looking at fungal active mycorrhizal communities again, and what I was finding was about a 50% reduction in fruiting. So there was just half as many mushrooms in these islands as we would find in the same size patch in an intact forest, right? And I attribute that to just this drying effect. But having said that, I would never stop if somebody wanted to leave some individual trees because of whatever reason. I would never stop them. I would say, anything you leave behind is good. But I think the consensus for something like ectomycorrhizal fungi is that an aggregate is a more stable habitat. It's likely to last longer, less fragmentation pressure, also less likely to blow over, right? There's always an issue with individual trees. Sometimes those blow over.
Yep.
That demo, I think it's called demo study in Washington State, they suggested a hectare as sort of a minimum. From my point of view, and then they're looking at everything, birds and plants and all that stuff. But from a fungal point of view, I was coming in around 0.3 of a hectare. I don't know what that is in acres, sorry. So that kind of medium-sized patch, I think it could be really effective. And then the other part of it is I did some work on species area curves. Like, okay, so this 0.3 of a hectare patch works great, but how many of those patches do you need to keep all the species, right? And it's a surprising small amount. So even like 10% of the forest, if you left it in patches, seems to capture all the species, at least one, maybe not. We can talk about minimum population size, but basically a small amount of retention goes a long way for something like fungi, for sure. And I think that's a really positive message for forest management. You don't have to put half the forest aside necessarily. A small amount can go a long way.
I'm curious. I'm just learning about it. So this is really fascinating. This is really cool. Where do you guys see this going in the future? Where do you see research kind of expanding on this, or kind of like where do you picture yourselves or maybe others really trying to refine our knowledge on this?
Well, so I guess on the top of common mycorrhizal networks. So again, at the beginning we were talking, this is a very niche discipline. So I mean, already you can imagine, okay, there's only a few people in the world that study mycorrhizal ecology, say in forests, and then there's even a smaller bunch of people that study common mycorrhizal networks. But I think for that particular research community, what I see as the next steps as exploring just some really basic information in terms of what is the structure of these networks, which trees are connected, how many trees in a forest, how long do those connections last, which fungi are doing the connections. Like we have very, very little base information on that. So one of the things that came out in the review is those maps, those common mycorrhizal maps, what we call them, they've only been done in 5 studies in the world, and they capture only 2 tree species. And there's thousands and thousands of tree species. You think about all the forest cover in the world, and we have such a tiny, tiny, tiny slice of information. So I think building just the basic biology of these common mycorrhizal networks will be really important. And I think too of designing these field experiments where we can eliminate some of these confounding effects. But I also think what's really important is to rank the possible effect of these common mycorrhizal networks on resource transfer, on seedlings, in comparison to other things going on in the forest. Because I think one of the problems that have developed is that this idea of common mycorrhizal networks, it's super cool and all of that, but the effect it has on seedling survival could be like minimal, say, compared to how much precip falls in a year, or the genetics of the seedling, or herbivory, or whatever it is. And so it is getting a better handle on just like, where do these rank? Because I think, Marty and I both we said so far, there is just really no good evidence that they have any ecological relevance in terms of the seedling survival and growth. And so I think we need to do a better job in that. But again, this is just a little small discipline, a small subset of the wider discipline of like the role of mycorrhizal fungi in forests. And I bet I'm going to turn over to Marty, and I'm sure he has some good ideas of where that larger field is going to go next. And I think to me, that's also really interesting and important. Yeah.
Well, I mean, there's probably a few dozen topics people are undertaking. I think the one I kind of am most interested in is this idea of a ecological rotation. We have a good sense of what an economic rotation looks like in forestry. Okay, we're going to log this in 75 years. But the ecological rotation, how long does it take for that community to come back to that late seral condition? And again, I'm just focused on ecomycorrhizal fungi, even though there's all kinds of biota to stand. And I think it's quite clear that there's also a landscape context. So if you have a jack pine stand on sand, maybe there's 100 species there, and it only takes 50 years to come back because it's a community, it's an ecosystem that burns all the time, and it's got high turnover. And so it's it's a different situation. Now, maybe on the coast, you've got a Sitka spruce ecosystem that has 300 species, and it takes 200 years to come back because that's a system that's not used to burning. That's a system that doesn't disturb. And there's way more complexity and way more of these late seral species, right? Like, we can't just assume there's one number for every ecosystem in the world. It's got to have more nuance than that. So I think truly trying to understand our landscapes, we can kind of use this idea of an ecological rotation. Where does my forest type fit into that big picture?
Yeah, I like that ecological rotation. That's good, Marty.
Thank you.
Well, it reminds me of a lot of conversations we've had with various researchers talking about ecological forestry, natural disturbance regimes, or modeling silviculture after natural disturbance. And as you said, Marty, trying to maintain all the pieces, like Aldo Leopold said. I just like Brad, this is really fascinating for me, and it's something that I needed to learn more about. So I really appreciate both of you coming on and just kind of helping improve our understanding of what the state of the science is right now.
Well, you're welcome. I mean, well, I know I'm very passionate about this topic, and I really hope that, even with this maybe not like kind of disappointing message in that, the story is just way ahead of the science, but it doesn't mean that it needs to kill anybody's enthusiasm for fungi and forest and their curiosity. I don't know. I guess for me, I just didn't ever need that story to be really curious about forests and like to be in them. And I hope people can hang on to that too.
I agree.
Brad, that was a great conversation with Justine and Marty. I'm really glad that we had those two on.
It was great.
I know that we had promised Justine that we would not do mushroom jokes, but I heard you had a pretty good one.
Oh, yeah. Hey, why did the fungus children not want to get in trouble?
I have no idea.
They didn't want to get in a truffle. Huh? Get it? Huh? Whatever.
I'm sure Justine will love.
Whatever.
I'm sure she'll love that one.
I thought it was great. There's a reason we didn't use it, Craig. There's a reason we didn't use it.
So, anywho, we're told by Susan that our 2023 SilviCast stats have come in.
Oh, so we have 3 listeners, right?
No, we have apparently more than that, or else those 3 listeners are downloading a lot of times.
Well, we got your family, and we've got Michelle, and there's a couple people.
So we had 12 episodes in 2023, 19,500 downloads in 52 countries.
Well, that's nice.
And the number 1 download city is?
Well, it's got to be close to home, right?
Guess.
Number 1 city, Junction City, Wisconsin.
Go Junction.
Yeah. Shantytown? No?
No. Yeah, you're
I'm getting further away.
You're getting further away.
Yeah.
Yes.
What was it, Madison?
Yes, it was Madison.
Yeah, that makes sense.
So thank you, SilviCast audience. Hope you tune in again this year. Thank you for tuning in 2023. We learn, Brad and I, as much as you do, and have fun putting these episodes together. So I'm just glad that you're all listening.
Yeah, me too. And thanks for listening to today's episode of SilviCast. If you have ideas for future episodes, question for the Dropbox, or anything for us, just let us know. You can reach us at UW Stevens Point's Wisconsin Forestry Center by emailing wfc@uwsp.edu, and you can find that on our website as well. Feel free to include a sound file of your question or a comment if you like. We'd love to use your voice as a part of this. And don't forget, we learn best when we wrestle with questions, so keep them coming.
You kind of mixed up that closing a little bit this year, Brad. Nice job.
You like that?
Yeah, yeah. So take care, everyone. And as always, thanks to our team, Susan Barrett, editor-in-chief, Joe Rogers, our IT master, theme music by Paul Frater, and of course, UW Stevens Point's Wisconsin Forestry Center.